Hi everybody, my name is Raul Casas and I'm a systems architect with the IP group at Cadence. Last week we talked about a methodology for reducing the complexity of convolutional neural networks. We created an optimization problem where we minimized a cost function, f of x, by playing with the parameters x, which were the dimensions of the neural network. So we're minimizing f of x, which is the cost, over the parameters x, such that the accuracy of the network is above a certain threshold. So today, I'm going to be talking about the results that we achieved with this minimization process. And first, we talk about the handwritten recognition benchmark, MNIST, where we apply this methodology over several iterations. At the first iteration, we have the original network that consumes 2.3 million multiply accumulates in the convolutional layers to achieve a result of 99.19% accuracy of recognition of these handwritten digits. So once we applied the methodology in the first iteration, we achieved slightly better accuracy, and that's perhaps because there are less parameters now to deal with. With less parameters and less complexity, we're now at 1 million multiply accumulates per image. And that gives us a reduction factor of 2.2x. We apply the method again, and by the second iteration, the accuracy drops a little bit below the original accuracy. So we decide to stop there. The number of multiply accumulates is now 0.6 million, and that gives us a reduction factor of 3.5x. So this was successful, and we decided to apply this to more interesting, more challenging problems. So we moved on to the German traffic sign recognition benchmark. And there, we created a new network, which we call the Cactus Network, where we throw in a lot more dimensions to play with, a lot different convolutional layers with different input-output dimensions and ways to reduce the complexity and still maintain the accuracy. And we apply this methodology, we do it for several iterations, and we compare against the hinge loss algorithm, which is in the literature the algorithm achieving the most accuracy. And that algorithm uses 1.4 billion multiply accumulates. We're able to achieve with superior accuracy, but 34 times less computations, the same performance. So now that we have some success with this German traffic sign recognition benchmark and this Cactus network, we moved on to an even more challenging problem, ImageNet, where in ImageNet we have 1 million different training images over 1,000 different classes of images. And here we have a landscape of different networks, where we plot them on this complexity versus accuracy space. We have ResNet 50, which has high performance at a low complexity per operation. There are other networks, by the way. Inception ResNet V2, for example, has higher performance, but much higher complexity. So we don't consider those in the sweet spot of this space. For comparison, we also have VGG19, GoogleNet, and 3 different Cactus networks, Cactus A, B, and C, which are different iterations of the methodology. And so Cactus A has slightly better performance than ResNet 50 and is 2 times smaller than ResNet 50 in terms of computational complexity. Cactus B has slightly better performance than VGG19 and is 15 times less computationally complex than that network. And finally, we have GoogleNet, where again, our performance is slightly better, and the factor reduction in complexity is 1.8x. So you can see that this methodology works well in different scenarios and gives the complexity reduction that's required to operate in embedded devices. Thank you very much for watching, and see you next week.